All right. Good morning, folks. I hope you folks all had a good weekend. Glad I had a chance to meet with everyone this morning or today, and then hopefully what we'll be able to do is finish out this semester and try to cover as much of the gases as we can, and then we'll finish up next week. Okay. All right. So what I would like to do then is I want to use the PhET lab here. So the PhET lab is in front of you, and hopefully you had a chance to take a look at the PhET lab and get that done, and kind of play around with it a little bit to see how things work. But I want to use the PhET lab here first to review with you the properties of gases and go over with you the properties of gases. And we'll be able to see then on a microscopic level, and that's the whole idea behind this PhET lab, that you're able to see on a microscopic level how these particles behave. Okay? And so when we talk about gases, remember, we're talking about a state of matter in which the on the macroscopic scale, what we're able to observe with gases is that they have no volume and they have no shape of their own. Okay, and so let's go ahead and take a look at what happens then. So hopefully you had a chance to take a look at the PhET lab here and understand some of the controls here really quickly. So I'm going to go ahead then and I'm going to click the particles here, and then I'm going to pump the handle here. And so as soon as you pump the handle, let's go ahead and let's make some observations really quick before we make any we introduce in the gases. First of all, I want to draw your attention up to here, and that is that the pressure, we have our pressure gauge here, and the pressure gauge is reading 0. The units here are in atmospheres. Okay, so make sure hopefully you make note of that as well. They start out as atmosphere, but you can change them as kilopascals as well. Okay, I'm going to leave them in atmospheres because that's a little bit easier to work with. So we'll make note of that. Also, we're going to make note of the thermometer here, and at the initial state, the thermometer then is at 0. Okay, and so my question to you, and I'd like you to answer this really quickly on your paper. So answer this on your paper. My question to you then is, why is the pressure here at 0? Why does the pressure gauge read 0? Okay, and secondly, why is the temperature at 0? So effectively here we have 0. Okay, down at the bottom. And so what does that mean for what's happening inside the chamber here in terms of the kinetic energy? So why is the pressure gauge 0? Okay, and explain that. And why is the thermometer reading also 0? And make sure you answer that in terms of the kinetic energy. Okay, so go ahead and answer that. Okay. All right. So the question that I asked you is that why is the pressure gauge 0? Well, we said then that the pressure gauge is going to read 0 because remember the gauge here is measuring. The gauge is measuring then the pressure inside this chamber here. The pressure inside the chamber here is 0, and the reason for that is that there's nothing in the chamber. Remember, the chamber will only read the pressure gauge will only read something is if there are particles here moving around and colliding with it. Okay, so colliding with it and changing the pressure inside the chamber here. So inside the chamber here now we have effectively a vacuum, and if there is a vacuum in this chamber, remember with a vacuum we said then that there's nothing in there. There are no particles inside the vacuum. Okay? And so there's no particles inside the vacuum. There can't be any collisions. So there's no particles. There are no collisions. Okay? And so remember, we said that it's the movement of these particles and how they collide, how they interact with one another that leads to the forces, and those forces then lead to pressure. And so therefore, if there are no particles, there can't be any collisions. And if there are no collisions, and I'm sorry, let me go clean this up a little bit. If there are no collisions, then we can't have any pressure. So that's why the pressure gauge reads 0 here. Okay. All right. So hopefully you had a chance to answer that. So please make sure you write this down. So if you didn't get that, make sure you write that down so that you understand then that within a vacuum, the pressure will always be 0, whether it's 0 atmospheres or 0 kilopascals, because there are no particles. No particles, no collision occurs, and if no collision occurs, you get no pressure. Okay. All right. Let's go ahead then and let's take a look at the second question I asked you, and that is why is the temperature here reading 0? Okay, the temperature reading here is 0 because remember we said then that there's a relationship between temperature, and that temperature is a measure of heat energy. Okay, the temperature is a measure of the heat energy, And we said then that that heat energy, as we continue on, that heat energy is related to the kinetic energy of the particles. Okay, so the kinetic energy of the particles. Okay? And so the kinetic energy of the particles then, okay, results from the motion of the particle. And so we said then that the kinetic energy is the average kinetic energy of all the particles as they move in here. Okay, so the temperature then right now is reading is 0 because there's no heat energy in there. So if there is the temperature, if the temperature is 0, if the temp is equal to 0 here, 0 Kelvin, okay, which means then the heat energy is 0, and the units for heat energy is 0 joules. Okay, and so therefore the kinetic energy is also 0. Okay, so therefore there's no motion in here, which kind of goes back to what we were saying about pressure. You need motion to have pressure, but you need motion also to have temperature. Okay, so the fact then that the particles have to move, okay, is fairly important for us. The gas particles have to move is fairly important for us. Okay? All right, so let's go ahead then, now that we have that out of the way, let's go ahead then and let's see if what we say is true. Okay, so let's go ahead and put in the gas particles. Okay, and let's pause it right there. Okay, and as you notice, as soon as we introduce the gas particles into the vacuum chamber here, the pressure now gauge has a reading, and the reading is about 5.5 atmospheres, but there it is. The reason why there's pressure is because you have particles in here that are moving around. Now, technically, they haven't bounced off and collided with the pressure gauge yet, but the idea then is that if there is particles, if there are gas particles in here, then that's when you have pressure. Okay. Now, look at the temperature gauge here as well. Okay. As the particles move in, you have now motion. The particles are moving, and as they move, they create heat. They create kinetic energy. They kinetic energy within the chamber here, and that kinetic energy leads to heat, and heat then is going to correspond as the temperature here. Okay, so that's what we have with the SPET lab, and we see that now on a microscopic scale. We're able to relate then the macroscopic observations of pressure and so we're able to make a reading of the temperature of the thermometer. We're able to make a reading on this manometer here and be able to see then that the pressure here and the temperature here is related to the motion of these particles inside the chamber right here. That's what you have to be able to do, folks, and that's what I was trying to stress and emphasize to you in chapter 13, is that there is this connection between the macroscopic, what we can observe in our gauges here, our thermometer and our pressure gauge, and our measuring devices, and the motion of these particles here, which we cannot see. And so these gauges here, how we explain that is based on these motions here. Okay. All right, very good. So with that said, then as we take a look at these gas particles here, we notice then that they, as we push them into the chamber, they are filling now this chamber. They are moving around inside this chamber here. So they assume the shape of, essentially the shape of the container, and they also assume the volume of the container as well. You notice here, the shape of the container is basically a square, and they move into the square, and they fill in this space. And so these particles then, these gas particles then, are moving around, and we talked about the movement here is translational motion. And let me just pause it right here for you. Translational motion meaning that, folks, remember we talked about this. Translational motion meaning then that they move from point A, and let's go ahead and designate this. They move from a point here. So let's take a look at this gas particle here. It moves from this position here. Okay, so let's go ahead and let's mark this position right here. This is then its starting position, and we'll call this start. So it starts right here. I'm going to unpause it, and we're going to see where it ends up. Let's go ahead and unpause it, and we're going to follow that particle just for a little bit. Okay. Okay, pause it right there. This is the gas particle that we're looking at right there. Okay, so with that said, then the gas particle then ends up moving to this position here. This is where it finishes within that small time frame that I had indicated. So it moved from this start position to that end position right there. That's what we refer to as translational motion. And because of that, we refer to that as flowing. The gas particles flow, and let me go ahead and erase this here. They flow because they move from one position to another. Okay, they move from one position to another, and as a result of that, free motion, then they also flow throughout this chamber here as well. Okay. All right, and then what we'll notice here is that these particles are spread very far apart from one another. Okay, they're spread very far apart from one another, and that if we notice here, and I'm going to move this handle right here, and we saw this, if I move this handle right here, we can then compress the gas particles. And if you notice then they continue to fill in that space here, but we can compress the gas particles. If we continue to do this, are easily compressible. However, there is a limit to that compression, how much we can compress, and we'll talk, hopefully be able to talk about that later. But with that said, then what you're going to notice is, I'm going to open this up again. Okay? What you're going to notice then is, as we open it up, they're going to fill in that space as well. Okay? So they're easily compressible because there's a lot of space between these gas particles here. And then finally, what I want to draw your attention to then is that these gas particles are not attracted to one another. They bounce off each other, and you've noticed they collide here. If you notice, as they go through, they collide. And the other thing I want you to notice is, as they collide, they move at the same speed. They collide and they move at the same speed as they do before and after the collision. That's what we refer to as the perfectly elastic collision. Okay? All right, so we know then that these gas particles, what we're going to do as we move forward and study the gases, we're going to assume then, and I'm going to pause this again, we're going to assume that these gas particles then are going to be small. They're going to be little spheres. Okay? They're going to move, and obviously they don't look like they're moving too rapidly here, but they're going to move in a random, rapid, and constant manner. So if you notice it, as they move, they're moving in a fairly constant manner. They're not speeding up. They're not slowing down. Even with the collisions, they don't speed up. They don't slow down. They maintain that same type of motion. Okay? And then finally, I want to point out to you then that these particles then, as they collide with one another, the collisions are perfectly elastic, meaning then that they do not lose any energy or any energy or velocity as they move around. Okay. All right. So with that said, then let's quickly talk about what happens when we speed up. Okay. So let me ask you this. First of all, let me ask you this, if we can consider this. I'm going to change the identity of the particles here really quickly. Okay, so I want you to make notice then that we have then the pressure then, and I'm going to let me go ahead and reset everything really fast. Okay, so let's go ahead. Let's introduce in the large gas particles again. Okay, and we have a pressure reading about what right now is 5.5. I think it was 5.5. Okay, we'll call it 5.5. And the temperature here, 1, 2, we'll call it about 2.5. Okay, what do we have right now? 300 Kelvin. Okay, so we have a 300 Kelvin and 5.5 atmospheres for the pressure. Okay, all right, and that's with the big gas particles. That's with the big gas particles. Let me go and clear those guys out. Okay, let me clear them out. Okay, and I'm going to switch over to the small gas particles here. And let's see what kind of changes happen there. So we're changing the gas particles. Okay, let's go ahead and change it. Okay, and what do you notice? Okay, first of all, it would have these gas particles are moving faster. Now they're moving faster because they are smaller. However, if you take a look at this, the pressure is still the same. Okay, and the temperature is still the same. They only appear to move faster because they're smaller and they have their momentum is going to be a little bit different. Okay, their momentum always have to be different, but the velocity is still going to be the same. Don't worry about what momentum is. Momentum is mass times velocity. Okay, so their momentum will be different. Okay, but essentially their kinetic energy is going to be the same. Okay, their kinetic energy is going to be the same because they're moving at the same rate here, and we know that because the temperature is still the same. The temperature is still the same, and the pressure is still the same. And so the pressure and the temperature does not change as a result of the gas, the type of gas that we put in there. Look, and let's go ahead and the type of gas, but let's go ahead and let's see how we can change. And I'm going to alter this. Let's go back to our large gas particle again. Okay. What does change the pressure? What does change the pressure and the temperature of these gases? Okay, so what affects, what factors affect the pressure of the gas here? Okay. Well, hopefully, when you had a chance to do the gas law labs, then okay, you were able to. They asked you first and foremost to go ahead then and change the volume here. But let me ask you to consider this. Okay, what if we added together? Okay, let's go ahead and let's add the orange particles. So we have 50 particles of the blue gases in there, and let's go ahead and add 50 particles of the orange gas. We have mixed together. We have a mixture of gases now. We know this is a mixture because you have two different types of compound, two different types of substances in here in the gaseous state. So they're moving around, and look what happened to the pressure here. The pressure went up. Okay? You have the pressure going up. The temperature still is the same. It's still about 300 Kelvin here. So adding in the extra particles, okay, adding in the extra particles increase the pressure, which makes sense, folks. Let's consider this. Think about a balloon. If you blow into a balloon, you're adding in more gas particles. You're increasing the pressure inside that particular chamber. Okay. Now let's hold off on what we're going to talk about here. We'll talk about that in a little bit. But if you notice here, the pressure did change because we added more particles. Okay. All right. So let's go ahead and let's take away the blue part, the orange particles there. And let me ask you. So that's one way. By adding more particles, the pressure changes. So we have more particles. There's a relationship between particles and gas pressure. So let's go ahead and do this. So number of particles is related to pressure. Okay, so as we increase the pressure, as we increase the number of particles, the number of the pressure also increases. Okay, so that's one relationship that we can make use of right now. Okay, all right. How else can we alter the pressure? Well, let's go ahead and let's see what happens here if we change the let's change the size. Okay, let's change the volume of the chamber. Okay, so I'm going to go ahead and I'm going to compress the gas. I'm going to push it in about halfway through. All right. So if you notice, what I did is I made the chamber smaller. Okay, I made the chamber smaller. And remember, in your fit lab, effectively what we did in making the chamber smaller is we reduced the volume. And if you notice here, the pressure also increased right there. So we also see then, okay, that the volume, okay, also is related to pressure. But if you notice here, it's going to be this inverse relationship here, where as we decrease the volume, the pressure goes up. But there is a relationship between volume and pressure, and hopefully you're able to see that, and we'll talk about that in just a moment. Okay, and we'll get that done. So let's go ahead then and let's scale this back. So we saw then number of particles. Let's bring this back to the original pressure, which is right about 5.5, right? So let's go ahead and open it up a little bit more. So if you notice here, by opening up the volume, by making the space bigger, the pressure goes down. So that explains the second relationship here. So we see then that number of particles affect pressure, volume affects pressure. What's the only other factor that we can consider then that's going to affect pressure? Let's go ahead then. And right now, what we've done is we have, the temperature has changed here. So we'll talk about that in just a moment. Okay. But let's go ahead then, let's consider what happens when we increase the temperature. So we notice down here, we have a little device here, looks like a little bucket, okay, that we can use to increase the heat or cool down. Okay, so that means then we make it hotter or we make it cooler. Okay, so if we make it cooler, let's go ahead and do this. We're going to atomize, we're going to remove, and what happens to the particles, folks? Okay, look at what happens to the particles. The particles will change the way they move. Now remember, we talked about the movement of these particles and they're random, rapid, and constant. But what we can do then is by changing the temperature, either by adding heat. Let's go ahead and continue to add heat. You look at the thermometer up in the upper right-hand corner. The temperature's going up to about 500. We are about, what, 540 Kelvin now. These gas particles move faster. Let's cool it down. Basically, by adding the ice here, we are removing, the temperature's going down. And as the temperature's going down, remember the heat content is going down. And as the heat goes down, look what happens to the particles. Okay? They slow down. So then, therefore, then the heat is being lost here because the kinetic energy is being lost here because heat's being lost. Kinetic energy is being lost, meaning the particles move slower. They have slower. They're not moving as fast. Okay? But look what happens to the pressure here as well. Okay? And so I'm going to draw your attention to that. Okay, so I'm going to heat it up again. Heating it up means then we're adding heat energy into the chamber, and as we add heat energy into the chamber, the temperature goes up. That's what we see. But look at the gas particles. The gas particles are moving faster, and as the gas particles move faster, and as the heat goes up, look what happens to the pressure. The pressure also increases. And so what we can conclude then, and we'll wrap up here, is that when we take a look at temperature, as the temperature increases, the pressure also increases. So there is also a relationship between temperature and pressure. That is heat energy. And I'm going to put in parentheses here, heat. there is a relationship between heat energy and pressure as well. And we're going to talk about those as well. So I'm running a little low on time, and I took some of your time this morning with our meeting. So I'm gonna finish up here, and we'll talk about the gas laws tomorrow. But all the gas laws that we're going to talk about is based on these three relationships here, and you need to make sure then that you remember those relationships here that we've talked about. And we will use this to talk about Charles' law, Boyle's law, and Gay-Lussac's law, and we see how then we can calculate for the pressures if we know then information about the particles or the volume or the temperature. Okay. So please make sure you play around with this PhET lab here and make use of this PhET lab to understand gas behavior, because it's really important and it's very, very helpful for you to, even while you're doing the gas laws, okay, very helpful to be able to use this to see what happens when you change, what happens to the pressure when you change one of these variables here, okay? So these are the factors that affect gas pressure. And I'm gonna pick up with this tomorrow, and then we're gonna, we'll finish, we'll continue the gas laws, and we'll start working out some of these gas law problems. But again, make use of these PhET laws, this PhET lab, okay? And so if you're able to understand these controls over here with holding some of these variables constant, that'll help you with the gas laws as well, okay? All right, so very good, folks. So let's go ahead. I'm gonna stop right here. Okay, make sure you take a look at the homework for tonight. It's a set A from chapter 14. Please make sure you get that done. And then what we'll do then is we'll pick up with this tomorrow, okay? All right, have a good day, folks, and I will see you tomorrow.